Hello friends, welcome to the session on oscillators. In this session, we'll be discussing about Hartley oscillator. We will see the circuit diagram of Hartley oscillator. We will see how the Hartley oscillator circuit works. And also, we will analyze the circuit to obtain the expression for frequency of oscillation and condition for oscillations. Friends, as you know that you are viewing this session on my YouTube channel, Learn with Prakash Kanade, and do subscribe to the channel to see many more videos in the subjects of electronics and computer science. So let us start the session with Hartley oscillator. We know that oscillator is an electronic circuit or device that is used to generate the AC output. Any oscillator circuit will not have any AC input, and still it is possible to get AC output at the output of the oscillator circuit. Hartley oscillator is an electronic circuit which is categorized as LC oscillator. So the frequency of oscillation in the Hartley oscillator is determined by the inductors and capacitors that are used in the tuned circuit of the Hartley oscillator. This oscillator was originally invented by the American scientist R. Hartley in 1915. And that is the reason this oscillator is being called as a Hartley oscillator. Hartley oscillator consists of a feedback circuit, and this feedback circuit consists of a LC tuned circuit where the two inductors and one capacitor is being used in the tuned circuit. This tuned circuit works as a feedback circuit in the Hartley oscillator. As we know that for any oscillator, what we require is an amplifier followed by a feedback circuit. So in the Hartley oscillator, the feedback circuit is a tuned circuit where the two inductors and one capacitor is used. Since in the feedback circuit, we are making the use of inductors and capacitors, and the values of inductors and capacitors are normally very low, and therefore the frequency that is being generated by the Hartley oscillator is a very high frequency. The frequency of several kilohertz or even megahertz can be generated by making the use of the Hartley oscillator. This oscillator is used as a radio frequency oscillator, and the frequencies in the range of 20 kilohertz to 30 megahertz can be generated by making the use of Hartley oscillator. It is possible that we can construct the Hartley oscillator by using a transistor amplifier or by using operational amplifier. Low frequency oscillations cannot be generated by making the use of the Hartley oscillator because the values of the inductor and capacitor are very low, and therefore the low frequency oscillations cannot be generated by making the use of the Hartley oscillator. This oscillator is being used whenever we require the higher range of frequencies. So radio receiver, radar receiver, television receiver, all such receivers will require the use of Hartley oscillator. Hartley oscillator generates sinusoidal oscillations. That is, the oscillations that are generated at the output of the Hartley oscillator are of sine wave in nature. Now let us go for the circuit diagram of Hartley oscillator. So every Hartley oscillator will consist of an amplifier. So this is a CE amplifier circuit followed by a feedback circuit. The output of the amplifier is connected to the feedback circuit, which is a tuned circuit, and the output of the tuned circuit is coupled back to the input of the amplifier. So this CE amplifier will have resistances R1, R2, RE, and RC. These are the voltage divider resistances. They will adjust the bias of the transistor. The emitter capacitor will keep the AC potential identifier equal to the ground level. The output is coupled through a coupling capacitor to the feedback circuit, and the output of the feedback circuit is coupled back to the input of the amplifier through the coupling capacitor. The feedback circuit is a tuned circuit which consists of two inductors L1 and L2 and one capacitor C connected as shown in the figure. So the circuit diagram for the Hartley oscillator would consist of a CE amplifier and a feedback circuit. The feedback circuit is a LC tuned circuit which consists of two inductors L1, L2 and one capacitor C connected as shown in the figure. Output of the amplifier is being connected to the input of the tuned circuit, that is the feedback circuit, and output of the feedback circuit is coupled back to the input of the amplifier. Resistances R1, R2, RC, RE are the voltage divider resistances. They are used to set the bias of the transistor. Coupling capacitors are used to couple only AC and they block the DC voltages. Now let us understand how a Hartley oscillator works. As I told you earlier that in case of any oscillator, we require the initial starting voltage, and the initial starting voltage is being provided by the noise signal which is present at the input of any electronic circuit. So this noise signal is initially amplified by the CE amplifier. And we know that whenever any CE amplifier amplifies the input signal, then it will provide a phase shift of 180 degrees. So amplifier will provide a phase shift of 180 degrees to all the frequencies of the input signal. Such signal is coupled to the tuned circuit, which is a feedback circuit. And this feedback circuit is a LC tuned circuit. And this tuned circuit will provide an additional phase shift of 180 degrees to only one frequency. That is the resonant frequency of this tuned circuit. And only for that frequency, you will find that the condition of positive feedback is achieved, because the C amplifier will provide a 180 degree phase shift, and this tuned circuit will provide another 180 degree phase shift. Therefore, there will be a total phase shift of 360 degrees, and therefore the condition of positive feedback is being achieved. Now, when the Barkhausen condition A beta is equal to 1 is satisfied, that is when the product of the voltage gain of the C amplifier and the feedback ratio beta of the feedback circuit is equal to 1. When this condition is being satisfied, then we know that the sustained oscillations are generated at the output of the amplifier. The frequency of oscillation will not depend upon the CE amplifier, but it will depend upon the components that are used in the feedback circuit, that is the components that are used in the tuned circuit. Therefore, the inductors L1, L2 and capacitor C will decide the frequency of Hartley oscillator. It is possible that we can analyze the circuit of the Hartley oscillator, and by analyzing the circuit of the Hartley oscillator, we can obtain the expression for frequency of oscillations and condition for oscillations. In order to analyze the circuit, we will simplify the circuit. That is, we will consider the equivalent circuit as shown in this diagram. Suppose the transistor amplifier is being replaced by the voltage source AV into VI with output resistance RO. And this is the feedback circuit consisting of the three impedances Z1, Z2 and Z3, and they actually represent the inductors L1, L2 and capacitor C. So from this figure, we can easily observe that the output of the amplifier is being coupled to the input of the feedback circuit, and the feedback voltage VF can be given as beta times VO, where beta is the feedback ratio. And we know that the feedback ratio beta can be written as Z1 divided by Z1 plus Z3, because we are obtaining the feedback voltage across Z1 divided by total impedance Z1 plus Z3 into VO. The impedance of the tuned circuit can be given as Zp is equal to Z2 parallel Z1 plus Z3, which is just nothing but Z2 into Z1 plus Z3 divided by Z1 plus Z2 plus Z3, and one can easily check it by looking at the equivalent circuit. Now we can redraw this equivalent circuit, and here we have considered only a voltage source minus AV into VI with output resistance RO, and this is the feedback circuit which is represented by the impedance Zp, and the voltage, output voltage is VO, which is across the Zp, and suppose the output current is IO. Now we can write this current IO as just nothing but minus AV into VI divided by RO plus Zp, which is just equal to VO divided by Zp, and therefore the same equation can be rearranged as VO divided by VI is equal to minus AV into Zp divided by RO plus Zp. And therefore we can write the expression for the gain of the amplifier A is equal to VO divided by VI, which is just nothing but minus AV into Zp divided by RO plus Zp. But Zp can be replaced by this equation, Z2 into Z1 plus Z3 divided by Z1 plus Z2 plus Z3. And therefore, we can rewrite the equation minus AB into Z2 in the bracket Z1 plus Z3 divided by RO into bracket in the bracket Z1 plus Z2 plus Z3 plus Z2 into Z1 plus Z3. Now we can find the expression for the loop gain. Loop gain is just nothing but the product of the voltage gain into the feedback ratio beta. So loop gain can be written as A beta. So when I multiply the above equation by beta, but we know that beta is just nothing but Z1 into Z1 plus Z3. And therefore we will get this product as equal to minus AB into Z1 into Z2 divided by RO in the bracket Z1 plus Z2 plus Z3 in the plus Z2 in the bracket Z1 plus Z3. Now we know that Z1 is the impedance of the inductor L1, Z2 is the impedance of inductor L2, and Z3 is the impedance of capacitor C. And therefore we can write Z1 is equal to JX1, Z2 is equal to JX2, and Z3 is equal to JX3. So when I substitute the values of Z1, Z2, and Z3 in the equation, then the loop gain A beta can be written as AV into X1, X2 divided by JRO. We are taking the J term common in the bracket X1 plus X2 plus X3 minus X2 in the bracket X1 plus X3. Now we know that for any loop gain to be real, the imaginary part must be equal to 0. And in this above equation, the imaginary part will be equal to 0 only when X1 plus X2 plus X3 is equal to 0. So this indicates that whenever in the tuned circuit we are using the three reactances, then at least one reactance must be negative. That is, there must be at least one capacitance. And X1 and X2 can be of the same type, but X3 has to be of opposite type. So when we put the X1 plus X2 plus X3 is equal to 0 in the above expression, then we can write the loop gain A beta is equal to minus AB into X1 divided by X1 plus X3. And because X1 plus X3 is just nothing but minus X2, and therefore we can rewrite this equation as AB into X1 divided by X2. Now we know that for any oscillator there is a condition, and this condition is being called as the Barkhausen condition. And according to the Barkhausen condition, A beta must be equal to 1. So when I equate this equal to 1, then we can write AV is equal to X2 divided by X1. That is, we can obtain the condition for oscillation by substituting the values of X1, X2, and X3. X1 is omega L1 because it is the reactance of L1. X2 is omega L2 because it is the reactance of L2. And X3 is minus 1 upon omega C1 because it is the reactance of the capacitor C1. And therefore we can write the expression AV is equal to X2 divided by X1, which is equal to omega L2 divided by omega L1, which is just nothing but L2 divided by L1. And therefore we can get the condition for oscillation as AV is equal to L2 divided by L1. That is, the gain of the amplifier must be equal to the ratio of the inductors L2 to L1. If this condition is satisfied, then only the sustained oscillations are produced in the Hartley oscillator. So where in the Hartley oscillator, while selecting L1 and L2, you have to see that this condition is being satisfied. Now we can obtain the frequency of oscillations. Frequency of oscillations can be obtained by equating X1 plus X2 plus X3 is equal to 0. That is, omega L1 plus omega L2 minus 1 upon omega C is equal to 0. Therefore, omega bracket in the bracket L1 plus L2 is equal to 1 upon omega C. And therefore, omega square in the bracket L1 plus L2 is equal to 1 upon omega C. So this is just nothing but omega square is equal to 1 upon L1 plus L2 into C, or omega is equal to 1 upon under root L1 plus L2 into C. And therefore, the linear frequency F can be written as F is equal to 1 upon 2 pi under root L1 plus L2 into C. So this is the expression for the frequency of oscillation. The frequency of Hartley oscillator is given by F is equal to 1 upon 2 pi under root L1 plus L2 into C. So frequency of oscillation will depend upon the values of L1, L2, and C used in the feedback circuit or tuned circuit of the Hartley oscillator. So thank you friends for viewing the session. Hopefully you have understood the working and the analysis of the Hartley oscillator. Thank you all for viewing the session.